I would now like to give an example of a parametric surface that can be described in 3 different ways. So this example is going to be a cone. And for this cone, we're going to let x be u, y be v, and then z of uv is the square root of u squared plus v squared. So you can think about the expression for the cone that we had before, that z of xy is x squared plus y squared. So I'm going to sketch this cone for a second. And the idea with this cone is that every point on the surface of this cone can be expressed as a z-coordinate that depends on an x and y coordinate. So here we have a point xy, and then on the surface we have z, which is a function of x and y. But that's not the only way that we can describe a cone. We could describe a cone using polar coordinates. So we could think of the point xy as being some distance r from the origin at an angle of theta. And so we could think of that coordinate as being r cosine theta and r sine theta, in which case the z is actually equal to r. So when we expressed a cone in polar coordinates, we just said z equals r. So now if I want to describe that surface as a parametric surface, I can let x be u cosine v and y be u sine v. So I'm thinking about u as being like r and v as being like theta. In which case, z is going to be u. Here, x, y, and z are all being expressed in terms of coordinates u and v. And we're letting u, which is acting like the radius, vary between 0 and 4, and then v, which is acting like the angle theta, vary between 0 and 2 pi. But again, that's not the only way that we can express a cone. We could also express a cone using spherical coordinates. So we could think about x and y being expressed in terms of spherical coordinates. We can think about them as being r sine phi cosine theta and r sine, that's rho sine phi sine theta. So here we can think about x and y as being, in this case, my r, my radius, is going to be 4. So this is going to be 4 sine phi cosine theta, and then 4 sine phi sine theta. And then we want to express z as z equal to r, and r is really what sits in front of the cosine v. So r is actually 4 sine of u in this case. So z equals r is 4 sine u. So we could express this as, for example, 4 sine of u. And now we've expressed x, y, and z in terms of u and v, where u is acting like phi, that goes between 0 and pi, and then v is acting like theta, which goes between 0 and 2 pi. So I'd like to show you how these plots look in CalcPlot 3D. So this first plot is going to be just x equals u, y equals v, and then z is the square root of u squared plus v squared. Now we're letting u and v be between -4 and 4. So we're expressing this cone on a rectangular domain. And so that's why you don't see kind of these circles being at the cutoff. We get these kind of parabola shapes. It looks like at the cutoff because this is expressing this cone inside of a rectangular domain. So it doesn't quite look like a cone yet, at least because of where it's cutting it off. So I'm going to express it instead in terms of polar coordinates. So here, x is equal to u cosine v, and y is equal to u sine v, and then z is equal to u, which is acting as my radius. And now you can see it looks a little bit more like a cone. Okay, now we've got these circular cross sections. Okay, u is going between 0 and 4, that's the radius, and then v is going between 0 and 2 pi. Okay, so that's one way we could express it. Or we can express it in terms of spherical coordinates. Okay, so here x is 4 sine v cosine u, y is 4 sine v sine u, and then z is just that radius again, 4 sine v. U is going between 0 and 2 pi, and then that's because u here is acting like theta, and then v here is acting like phi, going between 0 and pi.